So, hi there everybody, we're now on our last video on the fundamental theorem of arithmetic, and at last here we are going to prove now the famous fundamental theorem of arithmetic. So building up on the groundwork that we have, well, we have actually how many? 3 videos for that. We have the lemma 1, lemma 2, and the corollary out of the lemma 2. And then we're going to make use specifically in our proof the corollary. Okay, hopefully we can recall that, or we can watch the previous video before this. So let's have it. Okay, so here, theorem. So this is called the fundamental theorem of arithmetic. Okay, so the fundamental theorem of arithmetic. So every integer, it states that every integer, all integer which is greater than or equal to 2, okay, either is a prime or can be expressed as a product of primes. Okay, again, every integer um, starting from 2, okay, 2 or greater than 2 can be expressed as a prime, or is either a prime or can be expressed as a product of primes. So the factorization into primes is unique. It is said to be unique. So there's only one factorization of such primes except for the order of the factors. So we say that 2 times 3 is equal to 3 times 2. So um, one instance, 6 has a unique factorization. It can be expressed, since it's composite, it's not a prime, so it can be expressed as a product of prime. So 2 times 3, which is also equal to 3 times 2. So that's what the theorem states. So the next number will be 4. 4 is 2 times 2. Okay, product of primes. 5 is a prime, so it cannot be it may be expressed as a product of primes, but it's a prime, so we don't need to express that as a product of primes. So to prove this theorem, so we will need to first show by strong induction. So we're going to make use of the strong induction, the second principle of mathematical induction, that n is either a prime or can be expressed as a product of prime. So if you want, we can put that in writing. The proof. So first, what we will do with the proof, let's move it a little bit here. First, what do we need to do? We will show by strong induction that n is either a prime. That's the first statement of the proof, that n is either a prime or a product, or can be expressed as a product of primes, or let's say a product of primes. Product of primes. And we must know that n is greater than or equal to 2. Next part of the proof is that we're going to establish that there is a uniqueness of such factorization. So meaning there's no other factorization except that. So then we establish the uniqueness of such factorization. Factorization. Okay, so that's what we will do in this proof. Okay, so for the first part, again, for the first part, let's call this, anyways, let's call this your first part here. Okay, let's call this 1, and let's call this 2, to establish that there's a uniqueness of such factorization. So let's have number 1 first. So for number 1, so to show that, let's first state, show that p of n is true for every integer n in integer n which is greater than or equal to 2. So therefore we say that here. So oops, since 2 is a prime, so clearly the piece p of n, the p of a, p of, you know, yeah, the first part, the basic step of the truth. This is again of the proof rather. This is the strong induction of the strong version of induction. So p of 2 is true. Okay, there. So since p of 2 is true, we need to carry on with the p of 2, p of 3, and until p of k. So we will now assume that p of 2, p of 3, up until p of k. Oops, let's make that clear. P of k are true. That is every integer oops, 2 through k either is a prime. So it's either a prime or can be expressed, or let's just say, or a product of primes. Okay, so that's what we want to assume now, that p of 2 up until p of k is a product of or 2 through k. All integers 2 through k are either prime or product of primes. Oops. Okay. Okay. So since we assume that that's the case, so if then we say if k plus 1 is a prime, then p of k, oops, let's make it small letter, k plus 1 is true. So suppose that k plus 1 is composite. Okay, so suppose say if k plus 1 is a prime, then p of k plus 1 is true. So suppose k plus 1 is composite. So if it is composite, then we have k plus 1 is equal to a times b. Okay, for some integers a and b. Okay, where we say that where one a is strictly greater than one and b, and then a and b are strictly less than k plus 1. Now, what do we say next? Okay, so what do we want to say? Um, by the inductive hypothesis, by the inductive hypothesis, a and b either are primes, either are primes, or a product of primes. So in any event, so we say then, in any event, k plus 1, k plus 1 equals a times b can be expressed, okay, meaning they can be expressed as a product of primes. Product of primes. Okay, thus p of k plus 1 is also true. Okay, so then we say thus by strong induction, by strong induction, the result holds. Result holds for every integer, for every integer n which is greater than or equal to 2. So that's the first part of our theorem, of the proof rather. So let me explain this a bit, since I have just wrote them quite straightly enough. My pen is not that working well. So to show that p of n is true for every integer n greater than or equal to 2, actually before this we denote p of n as a statement that n, okay, is a that n is a prime or can be expressed as a product of prime. So I think I haven't wrote the statement here. Oops. Okay. Actually, this is the proof already. So okay. I forgot. P of n is a statement that n is a prime. Is a prime. Or a product of primes. Let's just say product of primes. POP. For now. For now. Okay. So P of n states that it is a statement that n is a prime or a product of primes. POP. So it is true for every integer n, which is greater than or equal to 2. So we now use the strong version of induction, the second principle. So we say that start with the first integer. So since n is a prime, so 2 is the first prime, so 2 is a prime clearly. So therefore p of 2 is true. The first statement is true. Okay, so P of 2 is true. Now assume P of 2, P of 3, up until P of k are all true. That is every integer 2, okay, through k up until this value k here is either, okay, is either a prime or a product of primes. So if k plus 1 is a prime, then P of k plus 1 must be true since it's a prime, right? So suppose k plus 1 is composite. So we're going to have this as contradiction. So suppose k plus 1 is composite, so it's the opposite. Then k plus 1 is equal to times is equal to this product A times B for some A and B, okay? For some A and B where A is greater than 1 and B is less than k plus 1. So it's between 1 and k plus 1. So by inductive hypothesis, we say now that A and B are either primes or product of primes. In any event, k plus 1 is equal to A times B because we say that k plus 1 is composite. So it should be in this form, A times B, in any A and B. It can be expressed as a product of primes. Thus, since it can be expressed as a product of primes, and since it's composite, so therefore P of k plus 1 is also true. And thus, by the strong version of induction, the result holds that for every integer n greater than or equal to 2, okay, that for every integer n greater than or equal to 2, okay, all of them can be expressed as a prime or a product of primes. Okay, so that's the first part of our proof, everybody. So the next part will be to establish the uniqueness of the factorization. Okay, so let's move here a little bit because we will need more space for our proof. Okay, where did we start? Here. Let's start here. Okay, for number 2. So we need to answer number 2 now. So number 2, we will be establishing the uniqueness of the factorization. So to establish um, establish the uniqueness establish a uniqueness of the factorization. Okay, so to establish the uniqueness of the factorization, we do this. So let n be a composite number. Let n be a composite number, or let's say let n be composite in that manner. Okay, let n be composite. So um, let n be composite with two factorizations into primes with factorizations with two factorizations into primes. So how do we state this in informal way? So we say that n is equal to p sub 1, p sub 2, until p sub r for some r, and it's also equal to q sub 1, q sub 2, up until q sub s. So what do we want to do? We want to show we will we will show that r is equal to s, and every p sub I is equal to some q sub j, where 1 is less than or equal to I and j, which is less than or equal to r. So that is to say, the primes q sub 1, q sub 2, up until q sub s are a permutation of the primes p sub 1, p sub 2, up until p sub r. Okay, so what do we have so far? So what do we want? We will need to establish the uniqueness of the factorization. So we will be letting n to be any composite number with two factorization of primes. So it has two ways to factorize. So it's not unique, it's two. So we're going to prove this by contradiction. So say n is equal to p sub 1 up until p sub r, which is also equal to q sub 1 up until q sub s. So we will show that r is equal to s, and that for every p sub I found in this factor is equal to the q sub j, which is equal to this factor, which tells that they're equal. They're equal. So the primes, okay, q sub 1, q sub 2, q sub up until q sub s, since p sub I is equal to some q sub j, meaning q sub 1 up until q sub s are a permutation. So when we say a permutation, it's just another arrangement of p sub 1, p sub 2, and p sub r. Okay, so how do we show this? So we want to show this as this. So first we will assume. So we will assume in a while. So we will assume that actually this is for convenience. So assume for convenience that r is less than or equal to s. R is less than or equal to s. So since we say p sub 1, p sub 2 times p sub r is equal to q sub 1, q sub 2 times q sub s. So therefore we say p sub 1 divides q sub 1, q sub 2 up until q sub s. So we say that p sub 1 is a factor of q sub 1, q sub 2, and q sub s. Right after this, by the corollary that we have studied a video before. So by that corollary, let's just so it say before, though it's not that good to say that, it should have a name. Okay, before, since this is the thing that's happening, so we say that p sub 1 is equal to q sub I, to a certain I, for some I. So what do? We divide both sides by p sub 1. So dividing both sides by p sub 1. So we get, so what do we get? So if you divide both sides with p sub 1, so imagine what we're going to have is p sub 1, p p sub 2 up until p sub r is equal to q sub 1 times q sub 2 up until it will reach a number which will it will wherein it will show like q sub I minus 1 times q sub I times q sub I plus 1 up until q sub s. So in this method, what we can see here, we stated that p sub 1 is equal to q sub I. So that is, actually we can cancel this p sub 1 here and then this q sub I over here. So that what we'll have is this. What we'll have in the end is p sub 2, p sub 2, p sub 3, up until p sub r is equal to q sub 1, q sub 2, um, up until q sub I minus 1 and q sub I plus 1. The q sub I vanishes because we cancel it in the line before. Okay, now what we'll do is now divide p sub 2 in for the right hand side. Divide p sub 2 on the right hand side and also of course for the whole equation. So again, by the corollary that we have learned a video before, so p sub 2 is equal to some q sub j. Okay, so how do we show that? After this, we will divide now divide p sub 2, okay, for the whole equation. Now divide p sub 2. Um, so again, by the corollary. So we say that p sub 2 is equal to this q sub j for some j. So what we need to do is to cancel p sub 2 from both sides. So what do we have? Canceling p sub 2 on both sides, we have just imagine from this part. So we can imagine that if we're going to cancel p sub 2, it can be cancelled over here, and there will be some q sub j here. So if you want, let's type that clearly. So we have p sub 2, p sub 2, p sub 3, up until p sub r is equal to q sub 1, q sub 2, until q sub I minus 1 times q sub I plus 1, and then there will be some certain q sub j plus minus 1, and we'll have a q sub j, and then a q sub j plus 1 up until q sub s. Okay, now what we want to do is to cancel out the p sub 2 now, since we say that it's equal to q sub j. Okay, it's equal to p sub j. So we'll cancel this p sub 2, and then we'll cancel this q sub j. Okay, and then after this, we cancel this process then, or rather we continue this process for all of it. Now we know now that or we have established that is for convenience a while ago, since r is less than or equal to s, continuing like this, we can cancel every p sub t with some q sub k. Let me put that in writing. Sorry. So with that in mind, since we have known that since r is less than or equal to s, continuing like this, we can cancel every we can cancel every p sub t with some q sub k. This yields a 1 on the left hand side, okay, at the end. So of course it will end up in the 1 because all the p sub 1, p sub 2, p sub 3 up until p sub n will be washed out from this from this um equation. So then the right hand side cannot be left with any primes. Okay, so from this then we say the right hand side cannot be left. Oops, let's make that better. Cannot be left with any primes since we have cancelled all the primes, right? Since the product of primes, let's call that product of primes, can never yield a 1. Of course, it can never yield a 1 because if you can think of it, our equation will be like 1 1 equals q sub 1 q sub 2 up until q sub I minus 1 q sub I plus 1 up until q sub up q sub. For the previous one we have q sub j minus 1, q sub j minus 2, up until we will reach some certain q sub j minus 1, q sub j plus 1, up until q sub s. Okay, so again, since the right hand side, this part here, the right hand side, okay, cannot be left with any primes since the product of primes can never yield a 1. So multiply any primes, the lowest prime is 2. So multiplying 2 with any other primes cannot and never going to yield us this value 1. Okay, thus we must have exhausted all q sub k's by now. So we say that thus we have exhausted. So this is a common term in math. When I say exhausted, you have you have um all the numbers are taken into consideration. So everything is exhausted. So we have exhausted all q sub k's, meaning you have used all within your power. Okay, within your power to try out every q sub case by now. So therefore we say therefore r is equal to s. R is equal to s, and hence the primes q sub 1, q sub 2 up until q sub s are the same, or instead of the word are the same, the primes are, shall we say, they are equal with the primes p sub 1, p sub 2 up until p sub r in some order. Okay, so meaning we can say that by the theorem, by the corollary that we used up above, or the process that we use up above, this one is just equal to this one, only that by commutative property they are not in order. So in some certain order, not entirely the same. So thus, therefore, thus the factorization of n is unique, except, okay, I think you know this, except for its order, except for the order of primes in which the primes are written. Okay, so actually this is the end of proof now. If you want, we can run through again for the whole proof. So let's have it. Okay. So we started over here. Actually, we started over here. So where was that? Here. So it's quite a long, it's quite a long proof actually. But we'll manage. I know that. Okay, here we go. So first, to establish the uniqueness of the factorization, we will let n, okay, this certain n, to be a composite number with two factorizations into primes. Okay, we have two factorizations. N is equal to all the p's, p sub 1 up until p sub r, which is also equal to all the q's, q sub 1 up until q sub s. So what we want to show here, and we have shown that, what we want to show is that r is just equal to s. R is just equal to s. And for every p sub I, it is equal to f to such p sub q. The primes q sub 1, q sub 2 up until q sub s are a permutation of the primes p sub 1, p sub 2, and p sub r. So it's just another arrangement of these um, factors here. Okay, now what we'll do next is for the convenience of everybody. So we'll assume for convenience that r is less than or equal to s. But of course, we want to show that r is equal to s. Since p sub 1, p sub 2 up until p sub r is equal to q sub 1, q sub 2 up until q sub s, p, we can therefore say p is a factor of this q sub 1, q sub 2 up until q sub s. And that's true because this is a single term, for example, and p sub 1 is one of its factors. Okay, so by corollary, by the corollary before, after dilemma 2, p sub 1 is equal to some certain q sub I. So this p sub 1 is equal to this certain q sub I over here, q sub I, in such a way that you can cancel them. That's by the corollary before. Dividing both sides by p sub 1, what do we get? We get this. Okay, so we cancel out the p sub 1, we cancel out the q sub I, since we know that they are, again, they are equal. Okay, so continuing in this process, what we have is this. After this, we have divided p sub 1 and then get rid of the q sub I. We'll also do this with 2. Okay, this is the last line. So now divide p sub 2 this time. Again, by the corollary that we have shown, we say now that p sub 2 is just equal to q sub I. Okay, for some, or q sub j rather, q sub j. Okay, this is a j. Okay, so what we need to do is the same old thing. Cancel p sub 2 from both sides. So what we have is this. Okay, p sub 2 are cancelled, and then q sub j is cancelled since we say that p sub 2 is equal to some q sub j. Okay, and then furthermore, since r is less than or equal to s, continuing like this, Actually, we can cancel every piece of t. We can cancel every piece of t with some piece of k. So this yields a 1 on the left-hand side of the equation. So you can see from the example before that if we are going to continue in this process here, we can get rid of all the p up until p sub r, but retaining some q's, okay, which is left. So then um, the right-hand side cannot be left with any primes because we have canceled all the primes, right? We have canceled all of them because we say that p sub 1, p sub 2 up until p sub r is equal to q sub 1, q sub 2 up until q sub s. So since with the right hand side we have 1 and we say that all of them are primes, so therefore the right hand side cannot yield the left, which is equal to 1. So since the statement, since a product of primes can never yield 1, so I think that's trivial, that any prime can never yield 1 because 1 itself is it's not a prime. But try to multiply factors and you will never ever get 1. Okay, ever. And then here, therefore we say that 1 is equal to q sub 1, q sub 2, with the missing q sub I, with the missing q sub j, up until to the missing q sub t, or q sub k. So then, if we're going to continue that, we have okay, therefore we have exhausted all the q sub k's. Okay, by now we have exhausted all the q sub k's by now. Let me fix that. So therefore, r is equal to s because r can never be less than s. So therefore, we say that r is equal to s, and hence the primes q sub 1, q sub 2 up until q sub s is equal to p sub 1, p sub 2 up until p sub r. So here's the equal sign over here in some order, some different order. Thus, the factorization of n is always unique. That's a key word. It's unique. So there's no other numbers. For example, we say that 6 is 2 times 3. And it's just okay with 3 times 2. Only that there's no other factors of 6, except of course 6 times 1. There's no other factors that we can have from that number, but the factors are unique. Okay, only that for the order of primes may be different. Okay, in the way they are written. Yeah, so I think you have seen this box over here. So that's the QED. So we have ended the proof already. Yeah, I think this is the best time to end the video now. That is quite a long video. I hope that you were there all the way, and thank you very much for watching. I hope you would like and subscribe to my channel for more videos. So thank you very much and see you soon. Okay, bye bye.